So a little bad news. There you have an exam next week. So it's going to be Tuesday, and we're going to just devote the entire lecture to the exam. So you come in, you take the exam, you're done. Yeah.
You said Tuesday.
Oh, sorry, Monday. Excuse me. I was thinking Tuesday, Thursday. No, it's Monday. This is Monday, Wednesday class. Monday. The bright side, there's a folder called Exam Review. I have opened these up. The review sheet. There's a practice. We're going to look at this a little bit. We'll look at that too. And then there's a key. So feel free to review those yourself. But we're going to get to it. I opened up this is the review sheet that has all the concepts that you might need. So it's hopefully everything. Hopefully I didn't miss anything. But notice it only goes up to 7A. So we actually started going over some of the 7B stuff already. Like that's the energy levels and the transition of an electron between them. So that won't be in this exam. We're going to look at it a little bit today. Well, maybe we can skip it. But anyway, it's up to 7A, and I believe 7A is just energy of a photon, wavelength, and frequency calculations, the basics at least. And that includes the photoelectric effect, understanding that stuff. Okay? So you can go through just to remind you all the stuff you need to know. Measurement, nuclear atom, mole, compounds, Coulomb's law, electromagnetic radiation. There's some laboratory stuff on here, but nothing major. So maybe you know the Tyndall effect. Maybe you know what the difference is between a colloid and a solution. There's the labs. There's not a whole lot that we did that was brand new. We did kind of interesting labs that kind of went along with what we're learning, sort of. But like we hadn't done enough, so a lot of the labs are basic stuff. So it's just basic stuff. Okay. Okay. So I'll let you guys take a look at that. The stuff I was going to go over today, which I don't know, maybe we'll skip that. It's just more stuff that we've done already. So we've done up to this stuff. Like I believe we did this assignment where we calculated, right? We did these, right? Last week? Or no, Monday, excuse me. So since this is not going to be in the exam, I'm not going to continue and just go over this again. I'm just going to go straight to the practice exam, if that's okay. Just do a review. If you open it up, you'll come up to the same thing I'm going to see here. It's a Word document, and you can download it as a PDF if you want, or you can download it as a Word document, whatever you like to do. Let me make this nice and big so everybody can see. So let's just go through these, okay? Starting from the beginning. And these are very similar to questions you'll see in exams, on the exam. Some of them might not be great questions, which is why they're on the review now, but I try to make the questions better and not interpretable. They have exact answers. Anyway, which of the following correctly describes the difference between compounds and mixtures? Compounds contain more than one element, but mixtures do not. Well, the first part's true, but mixtures, that's not how that works. Compounds have a constant composition, but mixtures do not. That's true. So compounds mean a constant composition, meaning here's water, that's a compound. It is always 2 hydrogens for 1 oxygen. Or by mass, it's about 2 grams of hydrogen for every 16 grams of oxygen. All right? That's a constant composition. It's always that. Whereas a mixture, if I've got H2O and NaCl, table salt mixed together, I could have any ratio of sodium chloride to water. All right? That doesn't matter. There's no constant composition. So B, and it is easier to separate the elements in a compound than it is to separate the elements in a mixture. That's not true at all. To break apart water, I'd have to do a chemical reaction, which is a big deal. To separate mixtures, there's lots of ways, but for this one, I could just boil the water away and get the sodium chloride out. like that. That's it. So B is the only one that's true. Which of the following is not a physical property? So physical properties, remember, are properties that you can observe without changing or potentially changing the composition. So color, that's fine. Resistance to rusting. So this one's tricky because nothing's happening. It's resistant to rusting, but it's describing a potential to change. So that's not a physical property, the resistance to rusting. It's a chemical property. The fact that it's inert, the fact that it won't react, is a potential to change. So that's the chemical property. Density, mass, those are physical properties. Extensive properties. These are properties that change based on the amount of stuff. So density, temperature, flammability, melting point, those all are intensive. They don't change if you add more stuff. It's the same value, same property. But a mass, if I've got 2 grams of lead and I have more of it now, I'm going to have more mass. So that's the extensive property. Which of the ones do not belong? For that one, you don't even know what the definition is. You just have to kind of figure out which one's does not belong. Okay, so here's basic, actually dimensional analysis if you want to handle it. You don't have to remember any formulas. So I have a mass, I want to know its volume, and I'm given a density. You don't have to remember the density formula. All you have to remember is that whenever you see a compound unit like this, where you have a unit in the numerator, a unit in the denominator, that's a conversion factor. Think of density as being a conversion factor between grams and milliliters. So I could do this, I could flip it and use it. So I'm going to take my 63.49 grams. I don't want grams, I want milliliters of volume. So I need grams to cancel, I need milliliters on top. That's density just inverted. So there you go, that's the math. If you care about formulas, I mean, the density formula is density is mass over volume. And then you can do algebra. But I think the dimensional analysis method is a lot easier. So it's up to you. That doesn't work very well. Oh, I guess I didn't solve it. So 63.49 divided by 2.71, 23.4. Really? Did I get a number wrong?
2.70.
Oh, 70, not 1. Okay, sorry. Oh, yeah, 23.5. That's better. Yeah. Okay. This one's not very good either. That's better. Okay. So scales, smallest to largest. This is just a matter of knowing your prefixes. Smallest, in this case, nano, then micro, then macro scale. So this isn't not exactly a prefix thing, but it's related. When we talk about microscale, we're talking about things you can see in a microscope. Cells. You can't see atoms in a microscope. It's impossible. So that's the nanoscale. And our macro scale, that's the generic term for what we can see at our level. Okay? So D, that's smallest to largest. Which of the following represents a pair of allotropes? So that's a term I didn't really use much, but when you're talking about allotropes, these are different forms of elements. So an element is defined as a material that is made of one kind of atom, whether it's one atom by itself or a molecule. And so ozone and oxygen, this oxygen, the gaseous oxygen is O2. Ozone is O3. They're both made of one kind of atom, just O, but they're different forms of that element. So these are allotropes. Graphite and diamond are allotropes. They are both forms of carbon. It just has carbon in them. So A, that's it. All the others are molecules or isotopes. So this is not describing a material, or at least different elements forms. This is describing different, like, atoms themselves. The same element but different numbers of neutrons. Those are isotopes. Okay. So which of the following is not a metal? Okay. So on the periodic table, everything on the left side is a metal, except for hydrogen. Everything down here is a metal. All this is a metal. The diagonal line, excluding aluminum, aluminum is a metal, but everything else on the diagonal line is a non-metal, or sorry, semi-metal. And then everything on this side of that line, and hydrogen is a non-metal. So, gallium. Oh, no, I didn't mean gallium. That's a metal. Silicon. I'm thinking germanium. Silicon is not a metal. Keep germanium and gallium confused. All right, silicon is a semi-metal, not a metal. All right. How many of each type of atom does the compound contain? Well, 3 calciums. This 2 applies to everything inside the parentheses, so 2 phosphoruses and 2 times 4, 8 oxygens. So B. Hopefully that's an easy one. All right, now we have a conceptual question here. I've got hydrogen, the diatomic hydrogen, H2. But hydrogen atoms exist as H1, hydrogen 1, and hydrogen 2, sometimes called deuterium. And these are their relative abundances. 99.9% this one and 0.01% this one. Which is the most likely combination found in nature? So if you get H2, what is it most likely going to be made of? Is it going to be 2 H's, an H and a D, or 2 D's? Hopefully you would say H2. Deuterium is so rare that, yeah, you might find randomly a few of these, and H can attach to deuterium. That would be rare. Even more rare and super unlikely would be to find 2 deuteriums attached to each other, because they're already rare. The fact that 2 deuteriums will find each other and make a molecule is super rare. So the most common thing is H2. And that's just the nature of hydrogen. Most hydrogen is hydrogen 1. So what's the difference between carbon 14 and nitrogen 14? They have different numbers of protons. They're 2 different elements. So A is out. They don't have the same. And as far as neutrons, that's not the number of neutrons. That's the mass number. That's the protons plus the neutrons. So for carbon, if I subtract the number of protons, I get 8 neutrons. And for nitrogen, if I subtract the number of protons, I get 7 neutrons. They have different numbers of neutrons, too. So B is out. Here, this is carbon 14, this is nitrogen 14. So they have the same, they have, the C is wrong too. Nitrogen 14 has 1 more proton and 1 fewer neutron than carbon 14. So it's D. Yeah?
But we have the periodic table for the exam.
Yeah, you'll get this one.
Okay.
Yep. All right, zinc 2 plus ion that has a mass of 65 AMU. What would you say about it? Well, if the mass is approximately 65 AMU, then the mass number is going to be approximately mass 65. Okay? Well, it's going to be 65 exactly. If the mass is approximately 65, the mass number will be 65. So zinc is number 30. It's got 30 protons, excuse me. So it's one of these 3. If I do 65 minus 30, that's 35 neutrons, which is all of these are fine. So electrons, if it's a 2 plus ion, it's missing 2 electrons. So remember, electrons are negative. If it's a plus charge, it's missing electrons. So this is missing 2 electrons. So 30 protons, missing 2 electrons would be 28 electrons. Or you can do protons minus electrons, 2. So it's A. All right. I hope these are super easy for you, for most people, because that should be review. If a nanometer is 10 to the minus 9 meters and a millimeter is 10 to the minus 3, how many nanometers are there in 1 millimeter? You know, if you can't do that in your head, you can certainly do it on paper. So how many nanometers are there in 1 millimeter? If I have 1 millimeter, I can do millimeters to meters. So 1 millimeter, there's 10 to the minus 3 meters. And then I can do, so that cancels, and then I can do meters to nanometers. 1 is 10 to the minus 9. So if you do the math, you should get 10 to the 6th, I believe. Yeah. How many nanometers are there in 1 millimeter? You end up with 10 to the 6 nanometers in 1 millimeter. So E in this case. Feel free to do the calculation in your calculator, but that's not too hard to do. All right. Next, express this number using 2 significant figures. So, trailing zeros are never significant. So if I drop the 1 and make this a 0 instead, then all of the zeros would be insignificant, and there would be only 1 sig fig. So I cannot show this number using standard notation with 2 sig figs. I have to first turn it into scientific notation. So that number, 10,001 in scientific notation, is going to be 1.0001 times 10 to the 4th power, because I'm moving the decimal 1, 2, 3, 4 spots. And then rounding it to 2 sig figs, I'll just cut this part out. And since that's a 0, I'm going to leave this alone. It's 1.0 times 10 to the 4th. So it's B. All right, so sometimes you can't show a number using standard notation with the correct number of sig figs. You have to turn, ooh, what's going on? Jump to my cursor. Okay, so the appropriate number of sig figs in the result, 15.234 minus 15.21 is, let me put that in your calculator, see what happens. 15.234 minus 15.21. The calculator spits out 0.024. But this is subtraction, so we're going to go by the term that has the smallest, their smallest sig figs position. We're taking the leftmost of those. So this is the thousandths position. This is the hundredths position. Hundredths is more leftmost, so we're going to keep up to the hundredth position. And so actually this number 4 is not significant anymore. We're going to drop it, and since it's a 4, we're going to leave the 2 alone. It's 0.02. So how many sig figs does this have? 1. It has 1 sig fig, so A. That can happen. You can have numbers with a ton of sig figs, and when you do a subtraction, you've got 1 left. That happens. All right. So this one, we'll do it in steps. We're going to multiply those 2 things first. So 3.8621 times 1.5630. Calculator, I'm going to write the whole thing. Spits out 6.0364623. But how many sig figs should it have? Well, this has 1, 2, 3, 4, 5. The second term has 1, 2, 3, 4, 5. 5 is the smallest number. I'm going to keep up to 5. 1, 2, 3, 4, 5. So I'm going to put an underline just to remind myself that that's the last sig fig, but I'm not going to round. Not yet, because we're not done. Now I'm going to subtract 5.98. And the calculator spits out 0.056463. Now, the last sig fig in this term was the 10,000th position. The last sig fig position in this term was the 100th position. So we're going to keep the leftmost, hundredths, is further to the left than 10,000ths. So we're going to keep up to hundredths. That's it, that 5. And so since the first digit we drop is a 6, we're going to round that 5 up to a 6. So that 6 makes the 5 round up. And that's it, that's the answer. 0.06 is another one where the subtraction just kind of takes away all your sig figs. It can happen. All right, so A. Okay, so calculate the number of carbon atoms in a mole of sucrose. Oh, the subscripts kind of went away. So let's do that over on this side. Let me rewrite it so it looks nicer. So sucrose is C12H22O11. And if we need a number of carbon atoms, but we're starting with a mole, 1 mole, if you can read that of this stuff, I need to, so I don't care about the sucrose, I care about just the carbon. So this is where I need to convert my moles of one thing to moles of something else, and you always use a molar ratio to do that. So I need moles of sucrose to cancel out, and I need to find the moles of what I'm interested in, which is just moles of carbon. And where do I get this ratio? In this case, I get it from the formula. So one of these formulas has 12 carbons in it. So this cancels out moles of sucrose. I have moles of carbon, but I actually don't want moles. I want the literal number of carbons. So I'm going to use Avogadro's number. So 6.022 times 10 to the 23rd per mole. And so all of these atomic masses were a red herring. You don't need them. So 12 times 6.022 e to the 23, 7.2, so times 10 to the 24. Yeah, so D. Yeah, the superscripts kind of went away for some reason. That's weird. Okay. Okay. So far, so good. Which one of these is not true? So here's more mole-mole conversions, molar ratios. If I have 2 moles of CCl4, it contains 1.204 times 10 to the 24 carbon atoms. Well, let's just try the math real quick, see if that makes sense. 2 moles of CCl4. Well, they're converting it somehow to carbon. So again, if I'm starting with one substance, but I want a different substance, I need to use a molar ratio. So let's convert my moles of the stuff I have to moles of what I'm looking for. And I can get this ratio from the formula. So one of these, there's 1 carbon in them. And then once I have moles of carbon, now I can use Avogadro's number to get the actual number of those atoms. So this is the math. So 2 times 6.022 to the 23rd, I get 1.2 times 10 to the 24th. That's true. That works. So we just have to keep going through. I think you can kind of see, maybe, what's not going to work. Maybe. Well, let's see. So B, I've got a quarter mole, 0.25. I'm going to leave the zeros off for now, of CCl4. And I'm turning it into atoms of chlorine. So I don't want CCl4, I want chlorine. We need a molar ratio. So let's cancel out those CCl4 moles. Instead, let's get the chlorine moles. This ratio is different. There's 4 chlorines in every one of these. And then finally, Avogadro's number. So 4 times a quarter is 1, times Avogadro's number is Avogadro's number. Perfect. B is good. C, I'm going to tell you is good. D is good, and the one that's wrong is E. So 1 mole of CCl4, you're going to have to multiply this by 4 over 1 to get the chlorine moles. And then by Avogadro's number, it's going to be bigger than this after that. The actual answer is 4 times this. So I'll let you guys try the math if you don't believe me, but E is the one that's not true. Those are the worst, right? When you do the last one is the correct one. All right. Question, just stop me if I'm like going too fast, you don't understand something. So which sample contains the fewest atoms? Well, you can do the math of all of them, or we can just think about it. So number of atoms is based on moles. It could be one calculation just to see. So if I use carbon, 10 grams of carbon. Well, I want number of atoms. So let's convert the grams of carbon to moles of carbon using the molar mass. That's from the periodic table. And then I would multiply this by Avogadro's number. All right, that's going to give me the number of carbon atoms. Now, this math is not going to change for all of these. The only thing that's going to change is the mass is going to be the same. The Avogadro's number is going to be the same. The only thing that's going to change is the molar mass. So the one that's going to give me the smallest number of atoms would be the one that has the largest molar mass, right? Because if the denominator is really, really big, that's going to make this number small. So really we want to pick the one that has the largest molar mass. So between carbon and neon and fluorine, nitrogen, oxygen, neon has the highest molar mass. So neon is going to give us 10 grams of neon. It's going to give us the smallest number of atoms. Does that make sense? You can do the math. You can calculate it all out, and you'll find out that neon is going to be the smallest number of atoms for 10 grams. All right, light. We have green light with the frequency. What is the wavelength? So you should be like, no problem. We've done this to death, sort of. Frequency versus wavelength. We use the equation that has speed of light in it. And you can rearrange that. So if you're calculating wavelength, it's going to be speed of light over frequency. So speed of light is 3 times 10 to the 8 meters per second. The frequency is 5 times 10 to the 14 per second. So divided by seconds again. And that gives me a wavelength in meters, which is fine because that's what we're asking for. 3 e to the 8 divided by 5 e to the 14, 6.0 times 10 to the minus 7 meters. So that's like 600 nanometers. That's like red light. Yeah?
So with the speed of light, is that going to be something we need to memorize, or is that going to be on the test?
That's going to be on the test.
Okay.
So let me actually show you before I forget. This thing started with something like that.
Okay.
So you'll see that, and I think, oh, it doesn't show it. There might even be like a spectrum with like colors and stuff. Well, not colors, but it'll say red, you know. We don't have a color printer for exams.
Will the equations be on the exam as well?
Yeah, well, some of them. So here, look. Just so you can see. We've got energy of a photon. Here's the one that I just used. So notice that the one that has energy of a photon to wavelength is not there, but you can derive it, or you can memorize it, or whatever you need to do. Okay. What else is there? Yeah, so we've got Coulomb's law, and K for Coulomb's law, Avogadro's number. Well, actually, this is Avogadro's number. This is the inverse for getting AMUs to grams. We've got the electron volts to joules that we just kind of went over. Planck's constant, h, speed of light. Yeah, so all this is there. If you've got a nice graphing calculator, a lot of the constants are actually programmed into it too. So if you know where to look. All right. So you've got 3 waves, and we're telling you that these are all visible. Which one is most likely to be red? So this is a little bit easier to see than the one that was on the slides, I don't know how many lectures ago. Red light, out of the visible spectrum, has the smallest energy. Therefore, it has the longest wavelength. So something with a really long wavelength, we don't even see the second peak, but it's pretty long here. This is a much shorter wavelength, and this is the shortest wavelength. So B, the longest wavelength. If they're all visible, that's most likely red light. It's got the longest wavelength. Okay. X-rays have shorter wavelength than ultraviolet rays. So which of the following is true? X-rays have a larger amplitude. That's not necessarily true. Amplitude is just brightness. Okay? You can make either one bright, doesn't matter. X-rays have more energy than UV rays. That's true. Okay? Energy and wavelength are inversely proportional. The shorter the wavelength, the higher the energy. So X-rays do have more energy. That's probably it. X-rays travel faster. No, they both go the speed of light. X-rays have smaller frequencies. It's the opposite. It's the shortest wavelength, but it's the largest frequency. So frequency and wavelength are inversely proportional. Frequency and energy are directly proportional. You can always look at the equation too. All right. So the answer there was just B, right? Just B. What is the frequency of light produced by a laser with a wavelength of that? So that's it's just a tedious question. You have to use this same equation, except everything's rearranged a little bit differently. And the other thing is when we plug in our wavelength into this equation, it has to match the units for speed of light. Speed of light has 3.00 times 10 to the 8 meters per second. So wavelength has to be in meters. So before we can use the centimeters wavelength, we need to convert it to meters. 1.23 times 10 to the minus 6. And centimeters to meters. 1 centimeter is 10 to the minus 2 meters. So 1.23 times 10 to the minus 8 meters. That's what I'll plug in here. And the frequency is something times 10 to the 16, I guess. 3 e to the 8 divided by 1.23 e to the minus 8. Yeah, 2.44 times 10 to the 16 per second. Per second, that's hertz. All right, so per second or hertz, either one would be fine. D is your answer. Okay. Okay. All right, everybody loves these kind of questions. We've got 3 statements. We've got to find out which is, or if any are true. So according to the postulates of the wave theory of light, that's the old one, bright yellow light has more energy than dim green light. Yes. Wave theory said it was the brightness that has the energy. It's incorrect, but that's how we thought about for the wave theory. So that one is true. According to the postulates of particle wave theory, so the modern current theory, bright yellow light has more energy than dim green light. So we have to focus now on wavelength. Where does green lie versus yellow? So remember the Roy G. Biv spectrum? Here's yellow, here's green. Energy goes up this way. So violet has the highest energy. So green light has more energy regardless if it's bright or dim, according to the particle wave theory. So this is not true. So a bright yellow light does not have more energy. Green light has more energy according to the particle wave theory. The 2 is not correct. So far, A is correct. Maybe E, we'll see. 3, according to the postulates of wave theory of light, green light has more energy than yellow light. Yes. Oh, sorry. Wave theory, not particle wave theory. So if it was just wave theory, the old theory, bright green versus bright yellow, they would be the same. Because if they're equal brightness, then they have equal energy. So this is not correct either. So only one. A. Only A is true. Alright. Those are always awful to wrap your head around sometimes. There's some formatting issues here, but we're going to write formulas and compounds names for these combinations of elements. So let's start. We've got beryllium and phosphorus. So you look on the periodic table, you look to find where they're located. Beryllium is a metal, phosphorus is a nonmetal. So we have to put them together as an ionic compound. And so we're going to be using ions to do it. So beryllium as an ion would be +2, since it's group 2. And phosphorus as an ion, you count over from the noble gases, -1, -2, -3. Phosphorus is a 3- charge. Do the crisscross rule. You're going to get 3 berylliums, 2 phosphoruses. That's the formula. And the name would be beryllium. I suck at spelling beryllium, but I think that's it. Phosphide. So plain nonmetals that you have ions for, just take the IDE ending. That's it. So phosphorus becomes phosphide. Yes, there's a phosphate, there's a phosphite, but those are the polyatomic ions. Those are the PO4 and stuff, PO3. This is just plain phosphide. Beryllium is a type 1 metal. We don't need a Roman numeral. All right, so now we have B. This is already giving you the clue that these are ions, so ionic compound. We'll do the crisscross rule. If you do that, you get 2 cobalts and two carbonates. And I should have given you the name for that one, but the point of an ionic compound is we balance out the charges. They need to add up to 0. So it's silly to write 2 and 2 when you can just write 1 and 1. 1 cobalt, 1 carbonate. They're fine together. So the formula is going to be COCO3. You don't need a parentheses or anything when there's 1. And the name of this thing is cobalt. And I'm going to skip a space for a second. The second thing is carbonate. But cobalt is a type 2 metal. You need a Roman numeral for it. And the Roman numeral is not how many there are. The Roman numeral is the charge. So it's a +2, so it's a cobalt 2 carbonate. C is same kind of thing. Sulfate is SO4. So I thought about whether I want to make you memorize it by the exam. We'll just keep it easy. You don't have to memorize polyatomic ions for the exam still. So I won't have a question exactly like this. I'll give you more clues as to what sulfate is if it's in there. But sulfate is SO4 with a -2. Iron 3 is saying you have iron 3+. That's what that means. So now that you know what the ions are, you do the crisscross rule. This becomes iron 2 SO4 3. So whenever you do more than one polyatomic ion, you need a parentheses around it. And what is this called? It's literally iron 3 sulfate. That's it. Okay. All right, I hope 25 is not too difficult either anymore. We did enough quiz stuff and homework and all sorts of stuff on this. But as far as what we fill in the table here, oxygen 18, it has 8 protons according to the periodic table. That's the atomic number. For neutrons, we can do 18, the mass number, minus 8, the number of protons, which is 10. For electrons, we look at the charge. Well, it's a zero charged element, no charge. So the protons equal the electrons. They balance out. Z is the atomic number. We need to remember that for Bohr's equation that we just learned, which is not going to be in this exam. So Z is the atomic number. It's 8, number of protons. And then A, the mass number, is listed right there. And the symbol is 18. It's the protons plus the neutrons. So for this missing element, we know it's 13, 14, 10. Number of protons, 13 is aluminum. And the mass number, well, that's the atomic number 2. The mass number is these two added together, 27. That goes right here. And then the charge. There's actually fewer electrons than protons. So it's going to have a positive charge, and the difference is 3. So this thing, 13 minus 10, is a plus 3 charge. So that's what you would write. You can also include the atomic number down here if you want. That's optional. Okay. So I was grading Lab 1, and I noticed a good number of people. What's going on? Not everybody got this one right. So just to make sure, what happened? Let's go over this one real quick. So we have 2 cylinders, and we have to write a measurement for it. So how much water is in cylinder A? Now, the exact number that you're going to write, that is interpretable, but it's the certain digits, everybody has to have the same one. It's definitely between 27 and 28, so it's 27, but we can also be certain that it's between 0.4 and 0.5. So we read always from the bottom of the meniscus, not this top curved part. We read the bottom part. So it's between 0.4 and 0.5. It's definitely 0.4. Everybody should have these 3 numbers. Those are certain, but all measurements have to have an uncertain digit. So that's the last marker. The next digit will be a guesstimate. Where is it between 0.4 and 0.5? Everybody will have a different number, but you have to have that number. So I'm guessing 7. Maybe 8, doesn't matter. But that's my measurement. It has to have 4 sig figs. Don't forget units. And then for cylinder B, we have different markings. This is 30, that's 31. It's between 30 and 31. So the 30 part is certain. Now the next digit, the tenths, is going to be our guess. Where is it between 30 and 31? 0.2 maybe? That's a guess. Everybody can have a different guess, but that's mine. And that's it. So these are our 2 measurements. When you add them together, what is the total volume when you empty A into B? Well, add those 2 together, you end up with 57.67. But remember, what do I add here? Well, the calculator thinks there's a 0 here too. We added 7. But in reality, we don't know what's there. So that's insignificant. This, our tenths here is our leftmost least significant digit. Here it's the hundredths, so we're going to keep up to the tenths. And since that 7 we're dropping is 5 or greater, we're going to round this 6 up to a 7. 57.7 is the sum. Okay. So what? These boxes are kind of messed up. What is the mass of a single C60 molecule in AMU? So, we're not dealing with isotopes here. There's no indication of any kind of isotopes given. So instead of an actual isotope mass, we're going to use the average carbon mass, atomic mass. So each carbon is 12.011 AMU, but we've got 60 carbons. So 60 times 12, 12.011 times 60, I get 720.66. This is exactly how you do molar mass, right? Grams per mole, but it's also how you get the mass of one molecule in AMU. So what is the molar mass of C60? Well, it's the same thing. But instead of AMU, it's going to be grams per mole. All right, so this is the distinction between what an average atomic mass is versus a molar mass. They use the same value, just different definitions of what the unit is, basically. So one molecule weighs this many AMUs. A mole of these molecules weighs 720.66 grams. That's a molar mass. So your friend states that since C60 is composed only of elemental carbon, a beaker full of buckyballs would contain C60 molecules identical to every other C60 molecule. Do you agree or disagree? So is every single C60 molecule identical to every other one? Well, hopefully you would say, well, remember isotopes. Carbon, I mean, the reason why it's not a perfect 12 or 13 or something like that is because carbon comes mostly as carbon 12, but there's a little bit of carbon 13 and an even smaller amount of carbon 14 that exists in the world. And so in those buckyballs, there's a decent chance of finding a C13 as one of the carbons in the buckyball. You could even find a carbon 14 in there. You might even find more than one carbon 13 in that buckyball. Most of it's going to be carbon 12. But not, I mean, the idea is a sample of C60 that has billions of molecules of C60, they're not all going to be exactly the same. Some of them will have some carbon 13 in them. And that will make them slightly heavier on average, but that's it. Does it kind of make sense? Okay. So what does the 12.01 underneath the carbon symbol mean? So two interpretations. Again, it is the mass of one carbon atom in AMU, or it's the mass of a mole of carbon atoms in grams. That's what 12.01 means. And it's the average mass, by the way, not just yeah. All right. I think everybody got 28 style questions, but I'll do it anyway. I've got time. I think I'm gonna go too fast, actually. Okay, so we've got two isotopes of copper, copper 65 and copper 63 and 65. We want to know what the actual mass of copper 65 is, or just basically prove that it's copper 65 as the other isotope. So how would we do that? Well, the idea is all of the isotopes' masses times their abundance added up together will give me the average atomic mass for copper, which we can look up. Copper's average atomic mass, according to the periodic table, is 63.546 AMUs. So the idea here is I could take the first isotope of carbon, which has a mass of 62, sorry, this is on top of this, 0.9296, multiply it by its abundance in fraction form or decimal form, 0.692, and then add to that the next isotope of carbon, which is this one, carbon 65. Now, we don't know its mass. I'm going to put a big X there. We don't know its mass, its exact mass. But do we know its abundance? We actually can figure it out, because we're being told that there's only two isotopes. So the percentages for all of the isotopes together have to add up to 100%. If there's only two, then I can do 100% minus that 69.2%, and that'll give me the missing percentage for the other isotope. So 100 minus 69.2, 30.8%. So that's going to be the relative abundance for that copper 65 isotope that I'm trying to find the mass of. So now I just got to do the math. I've got to find out what x is. So here I'm going to do this down here. I'm going to just kind of simplify first. 62.9296 times 0.692 is 43.54728. I'm going to not worry about sig figs too much at this point, but that's going to be plus 0.308x is equal to 63.546 AMUs. I want to isolate x, so I'm going to move this over to this side by subtracting. Right? Remember your algebra? Minus both sides. So that goes away, and I get 0.308x is equal to, let's see, 63.546 minus 43.54728, 19.99872. And now I divide both sides by 0.308. All right, so divide both sides by 0.308. This will disappear. 19.99 divided by 0.308 is 64.9309 AMUs. I'm probably in my sig figs are not quite right at this point, but that's the what x is. So that makes sense, because notice, this is pretty close to 65. That's the isotope's copper 65 mass, yes.
So where'd you get the 63.546 again?
From the periodic table.
Oh.
So the periodic table is like the answer to this equation. It's the average atomic mass. Yeah.
Okay.
Yep. All right. Now this only works because we're being told there's only two isotopes. If there was more than, if there was three, we couldn't do it. It would be a little more difficult, but there's only two. Okay. So we have two compounds, one ionic and one molecular. Right? Molecular is better known as covalent. So here are the two formulas. Which one is ionic? Which one is molecular? So that's ionic. Immediately recognizable because there's a metal and a nonmetal. That's molecular because it's two nonmetals. So that's I explained it. So do it in word form now. Both formulas describe the composition in a similar way. What is similar about the way these formulas describe a compound? Well, what's similar, you can honestly write almost anything here, is that they have subscripts that denote how many. That's pretty much it. But there's a fundamental difference between these formulas when it comes to ionic and molecular compounds. So for ionic compounds, we call these formula units. You can't say, a molecule of MgBr2, because there's no such thing as a molecule of MgBr2. You will never find one magnesium and two bromines in a little clump, and that's it. You'll never find that. What you'll find is a large clump of a bunch of magnesiums and a bunch of bromines in a ratio of 1 to 2. All right, so that's why we call this a formula unit, because there is no such thing as a molecule of MgBr2. But CO2 exists as a molecule. That's what we call the molecular. That's why they're covalent. That's what you get from covalent compounds. So the number of CO2s is literally, or the number of the atoms in that formula is literally the number of atoms in a molecule. Okay. So what mass of water contains the same number of atoms as 25 grams of aluminum? I like these a little bit because they make you scratch your head because you're not really, there's no straight method of calculating one or the other. But we're looking for a mass of water that has the same number of atoms as 25 grams of aluminum. So let's start with the aluminum. 25 grams of aluminum. Well, if I'm interested in the number of atoms of aluminum, I would need to convert this to moles first. And I'm going to do that using a molar mass. Periodic table is 26.98 grams per mole. And, you know, I could go all the way to actual atoms. I could use Avogadro's number. But I actually don't need to do that. Because remember that moles is a way to count atoms as well. It's a shortcut to counting. It's like dozens, right? Dozens is still a way to count things. It's just you're counting in groups of 12. So I would like to leave it in moles because it's a way to count things. And you're going to see why. It makes things easier. So let's just do the math because might as well. 25 divided by 26.98 is 0.9266 moles. Moles of aluminum. So yeah, it's not a literal number of aluminum atoms, but it's still a countable number. Moles is what you count. You're counting a big group. And the reason I left it that way is because we're comparing a number of atoms of aluminum to a number of molecules of water. But we don't have to literally count those individually. We can just use moles as a way to count. So if I need the same number of moles of aluminum, well, that's how many moles of water I start with, too. These two have the same number. So I'm using moles, but it doesn't matter. They have the same number. So I didn't have to go to the atoms or molecules. I could just go to stick with moles. And now it's easier. I don't have to use Avogadro's number. So how many grams of water is that? The mass of water. Well, this is where molar mass of water comes in now. I think it's about 18.02, 2 hydrogen and 1 oxygen. .7 grams. So 16.7 grams of water has the same number of molecules as 25 grams of aluminum has atoms in it. Now you wouldn't be wrong if you went all the way to atoms, you used Avogadro's number, but you'll notice that you'll probably, so here you will multiply by Avogadro's number to get atoms, and then here you'll have to divide by Avogadro's number to come back to moles. So just cut out that step. Don't need it. Okay. All right, our Coulomb's law stuff now. So, if you take a snapshot of a hydrogen atom, and it happens to look like that, you've got a diagram on the left, you've got a diagram on the right. They're both the same atom, but just different time periods. Let's answer the question. Which snapshot, A or B, has an electron whose potential energy is the lowest? So, you've got to remember our Coulomb's law. Write it down again. So, potential energy is some constant times the charge of one, the charge of the second, and the distance between them. So, if the charges are opposite, you're going to have a negative potential energy, right? So you have a proton, you have an electron. So yeah, in this case, it's always going to be negative. So which one's going to give you the biggest negative, the lowest number? Well, the smallest distance, the smaller d is, the smaller this denominator is, the bigger this calculation gets. So the smaller d is, the bigger this value gets, and it's going to be negative. So a really large negative, it's really low. So the B snapshot will have the lowest potential energy. If you want to think of it in terms of magnets, the closer you put the magnets, the stronger that attraction is. So that's a more negative potential. Okay. Yeah, so this one doesn't want you to use a calculator, but how much energy would be required to completely remove the electron from the atom when the electron is at a distance in snapshot A? Okay. So if you have snapshot A, I'm going to have to look up K because I don't have it in front of me. Is it in here, maybe? I guess not. All right, let me go back to the beginning real quick. K is 2.31 times 10 to the minus 18 joules times picometers. So the clue there is your distance has to be in picometers. There we go. And since the proton is a +1 charge, the electron is a -1 charge. That's Q1 and Q2, and our distance is going to be 1,000 picometers. Perfect. So our potential energy is going to be negative 2.31 times 10 to the minus 15, I think. No, 21, isn't it? Did I go the wrong way? Yeah, I went the wrong way. Sorry. 21 joules. Now that's potential energy. Pay attention to the question. The question is asking for how much energy would be required to remove the electron. That's talking about ionization energy. So ionization energy is always the opposite of the potential energy. So our ionization energy required to remove this electron is going to be just the same number, but positive. So that's the amount of energy needed to remove that electron. That positive is very important. It's not negative, okay? Suppose that the snapshot B occurred after snapshot A. So first A happened, then B happened. To get to B, would the atom have been absorbing or releasing energy? What would be the sign of the change in energy? So, where we are, there we go. So, this has a higher potential energy. This has a lower potential energy. We kind of cleared that up with A. And so if the atom is getting lower in energy going from A to B, how does it get lower in energy? It has to give up energy to get lower in energy. So it has all this energy it needs to get rid of to get lower in energy. So it's emitting. It is emitting energy. It is releasing energy. And so what would the sign of the energy be for this change? The change in energy for this atom would be negative. It is releasing energy, so it is losing energy. Okay? Where is this energy going? It's going to a photon. The photon is leaving, taking that energy with it. So that's why it's a negative change for the atom. All right, so here's another situation. So you have a helium plus ion. How does the potential energy of the helium plus ion compare to the hydrogen atom in diagram B? So they have the same distance, I believe, 250. Yeah, 250 distance for B. But what's different is the charge now. So where D is the same for both of them, and the electron, the electron is the same. They have a -1 for the electron. Q1 is different for both of them. Hydrogen has a +1 charge there. This thing has a +2 charge. So the potential energy is going to be twice as low. It's going to be twice as large, but it's negative, so twice as low. So how does the potential energy compare? Twice as low. How much energy would be required to remove an electron from that atom? Okay, so just another Coulomb's law calculation. Uh, 2.31 times 10 to the minus 18 joule per picometers. Q1 is going to be plus 2 now. And Q2 is still a single electron, minus 1. And the distance is 250 picometers. So the potential energy for this atom is times 2 divided by 250. Negative 1.848 times 10 to the minus 20 joules. And so the ionization energy, again, is the opposite. A positive 1.848 times 10 to the minus 20. So notice that that ionization energy is higher than this one. There's a 10 to the minus 21 here. That's 10 to the minus 20 only. So that's higher. So you need more energy to ionize a helium ion than a hydrogen ion. Okay.
This is the K constant is 10 to the minus 16 over there.
Oh, did I make a mistake? Is that what happened? Is this wrong over here? Oh yeah, I read it wrong. I'm sorry. 10 to the minus 16. Excuse me. All right. So go back and fix a lot of these. This will be 16. This will be 19. This will be 16, and that'll be 18. Okay. Thank you for warning me. Okay. Yeah, so we did that, E. So now we've got line structures, and we want to know so we have the structure for it, we want to know the line drawing. A little bit of quiz there. So look for carbon-carbon bonds, and everywhere you see a carbon-carbon bond, just do a line. So that hexagon, boom, 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 boom. Be sure to include the double bonds. So there's a double bond there, there's a double bond there, a double bond there. And how you show them exactly is not a big deal. Anything non-carbon, non-hydrogen, actually draw it. So there's an O and H. We include the H's on other atoms, but not on hydrogen. There's a nitrogen over here, and there's a H over here, and there is a carbon. So there's a couple ways you can do it, but commonly you can do that. And then carbon there, and there's a double bond opposite. So anytime you see a carbon, just replace it with a bend or an endpoint or something like that. That's it. Okay. So what wavelength of light in nanometers is needed for aluminum to emit electrons in response to light? There's a work function for aluminum. Identify the corresponding region of the electromagnetic spectrum for this wavelength of light. This is probably the last thing that we've covered that is going to be in the exam. So this is the photoelectric effect. So we're going to work backwards from the work function of aluminum. We have this 4.08 electron volts. And to get energy of a photon and to go from energy of a photon to wavelength so that we can identify the kind of light, we need to go to joules. So let's convert our electron volts to joules. And off the top of my head, I have no idea what it is. It is, yeah, it's not here. There it is. 1.6022 times 10, I'm running out of room here, 10 to the minus 19 is 1 electron volts. So let me just calculate that. We'll have it. 4.08 times 1.6022 e to the minus 19. 6.537 times 10 to the minus 19 joules. Okay, so that's the energy of a photon in joule. That is the energy required to ionize aluminum in joules. So the idea here is we need a photon that has at least that much energy. That's the minimum energy the photon needs. So let's find that minimum wavelength. Well, the wavelength of any photon, I can calculate it from the energy of the photon. Right? This is just the energy of a photon equation. I just rearranged things already. Energy used to be here, wavelength used to be down here. So I'm going to plug in this energy down here. That's the minimum energy I need to ionize an aluminum, make electrons come out of it. And up here we've got Planck's constant, and we've got the speed of light. So our wavelength, like the threshold wavelength we need, is going to be times 388 divided by this number is 3.04 times 10 to the minus 7 meters, which if I convert to nanometers, just to kind of give me a sense of where it is on the scale, there's 1 nanometer in every 10 to the minus 9 meters. So 304 nanometers. Now, I'm not going to say that's the minimum wavelength, because wavelength goes the opposite way when it comes to energy, right? So this energy and lower, this wavelength and lower is what will give me enough energy to ionize that aluminum. So this energy, this wavelength, is exactly this much energy for a photon. That's the minimum energy. If I give you a lower wavelength, it'll be a higher energy. So at least this energy. So where is this? This is pretty much on the border of UV and visible. It's pretty much UV, though. I don't think we can see this. So this is UV light. If you look at a spectrum, usually 350 is about the cutoff when we can stop seeing it. Sometimes even higher, 380, something like that. Okay? All right. We can keep going if you want. So there's extra problems. So, I feel like that's a good length for an exam. Maybe a little long, honestly. But these are the kind of problems you're going to see. Let's keep going a little bit until it's time. That's a little fast, so we got like 10 minutes left. So 34 is a great one. This is actually something we didn't talk about too much because it's definitely review. The difference between accuracy and precision. So you've got somebody measuring the volume of a sample, and there's 4 trials, four answers. Here's 4. So if we average them, you get so that's their trials, but if you average everybody in the lab's results, you get 12.49. So what can you say about all this data? So this individual person, Sarah's results, would you say they have low precision, high accuracy, high, what combination of things? So here's how I'd interpret it. Her results are all really close to each other. They all differ by a few digits in the last place, right? So that indicates to me high precision. Using the tools that she has, which measure out to 2 decimal places, every time she's measured it, she gets pretty close to the same answer. It's a little bit of variation, but pretty much the same. So high precision. So that's what precision is. It's repeatability of a measurement. You can get the same number every time, use high precision. What accuracy, though? So if you average her values averaged about 12.39, 12.4, which is not the same as the entire lab's average. So what I'd say is, instead of saying she's right, everybody else is wrong, it's most likely her calculations are not accurate. She's precise, whatever she's measuring, she's getting the same number, but it's not the same as everybody else. So there's some accuracy issue. All right, so high precision, greater precision than accuracy, basically. That's what I would say. Does that kind of make sense? Interpreting that result. Okay, 35. You have two piles of atoms, and these atoms have the exact same number of atoms in them. These piles, I should say. The first pile contains only sulfur. That weighs 27.44 grams. The second pile contains only carbon. What does it weigh? Just, I think everybody should be able to do this one. So again, it's the same as last time. Why go all the way to individual counts? Like, let's just count moles. So if the first pile weighs 27.54 grams of sulfur, let's get the moles of sulfur. We're going to use the molar mass, 32.066 grams per mole. And then that is .08, excuse me, 0.858, no, 9 is fine, moles of sulfur. So the first pile has that many moles of sulfur. That's counting, just groups instead of individual atoms. Well, the second pile needs to have the same number, same moles, basically. So what is it? Carbon atoms. So it's going to be 8.8589 moles of carbon. But what does that pile weigh? Well, let's convert this moles of carbon to mass. 12.01 grams per mole. And you can see the moles cancel that way. 10.32 grams. That's the mass of the second pile. Okay. 36 is great. Another review problem. So, review is in a intro chem problem. So doing cubic conversions, or even squares if you like those too. But I have a density of water, which is 1 gram per centimeter. What is the? Oh, actually, it's not. It's not cubic conversion. It's something else. It's just density. What is the mass of a cubic foot of water at this temperature? Oh, actually, I guess it is. So if I have a cubic foot, so 1 foot cubed, to convert from a volume into a mass, that's what this is for. This converts volume into mass, but I need the volume to be in centimeters cubed. So let's do that. I know how to go from feet to inches, and then inches to centimeters. I know that. Right? There is 12 inches in 1 foot, and then there is 2.54 centimeters in 1 inch. Now, you don't have to memorize that. And I recognize there's some people who weren't born here and don't know this American conversion. So if you still don't know those, that's fine. Ask me. But those are the conversions. But these are for standards. So if I convert feet to inches, that's not going to work. It needs to be feet cubed. So I have to cube the whole thing. Right? So cube this and cube this. 1 foot cubed becomes 1 cubic feet. And 12 inches cubed, well, I cube both things. So cube 12, and I get 1,728 inches cubed. And then the same thing goes for inches cubed to centimeters cubed. I got to cube these two. So 1 cubed is 1, inches cubed is inches cubed. 2.54 cubed is 16.387 or so centimeters cubed. So there's the full conversion. Inches cancel, feet cubed cancel. So 1 times 1728 times 16.387. I get 28,316 points. I mean, it keeps going, but that's probably too many sig figs. centimeters cubed. So how many grams is it? Well, it's 1 gram per cubic centimeter, so it's 28,000 grams still. Oh, we're not done. We got to go to pounds. What is the mass? They didn't say that, but in pounds. So finally, let's do the rest of it. 28,316.7 centimeters cubed. Let's do the density conversion. There we go. 1 gram per cubic centimeter. All right, that gets rid of that. Grams to pounds. You don't have to know that one either. You can ask if I don't provide it, but I should provide it. 1 pound is 454, approximately, I think. I'll list a better one, but that's a good one. So divide by 454, 62.4 pounds. Is that on there? Yes. D. Thankfully it's on there. Or else I did something wrong. So this is the hard part, is, how to go from standard conversions to cubic conversions if you're doing a volume, or squared conversions if you're doing an area. Okay? Okay. The likelihood of getting one of these is lower because it's review, but it could be there. 37 is another one, similar to the first one we did for this section. We have a series of measurements. They were made by different students. Which set is the most precise? So again, precision is repeatability. We're looking for numbers that are very, very close to each other. So one way to figure that out is to calculate a range. Take the smallest, take the largest. Which one has the smallest range? So I should say, take the smallest number, take the largest number, and do the difference between them. So this is pretty far all over the place. This is kind of all over the place. This is not that bad, but it's still 0.522 to 0.503. This looks like it's the closest to each other. D. They have the smallest range. So that's the most precise. D. How long would it take for 6.5 billion people to count out the number of molecules in a mole if each person counted 1 molecule a second? This is a conversion problem. So knowing how to do dimensional analysis. All right? This is definitely a valid question. So you have to understand, what do you start with, and what is a conversion, what is an equality. So we're starting with 6.5 billion people. So 6.5 billion, a way to say that in numbers is 6.5 times 10 to the 9. Right? Million is 10 to the 6. Billion is 10 to the 9. People. And you have some equalities. We have, if each person counted 1 molecule per second. And then we're saying, how am I supposed to do this? Hold on a second. I'm trying to think how to organize the dimensional analysis. I can do it in my head. I just can't. Let me think about how to do this real quick. Is that a better way to start? Probably. Yeah. I think that's the better way to do it. Yeah. Okay. So let's start with the Avogadro's number. And let's just make it 6 times 10 to the 23 molecules. Well, let's just see total seconds. If we counted 1 molecule per second, so 1 molecule in the denominator, 1 second in the numerator, well, it would take this many seconds, right? But we're letting 6.5 billion people count per second. I'm still doing it wrong. Dimension, I can't. This is the math right here. So multiplying this, no, that's not it. Divide by, that's what I'm thinking of. Let me come back to this. I'll post a solution to this if I can. My head's not working today. I'll come back to that. I think we're going to divide by that number of people, and it would work. But I can't explain exactly how, so I'll come back to that. But I think we're out of time. So these should have all solutions on the key, and if they don't, and you want to help with a solution, let me know, and I can add it. But these should be listed online. And my brain stopped working, so sorry about that. All right, we're going to stop there. Anybody have any questions? Yeah.
Would it be instead of 1 second per molecule, couldn't we do 1 person per molecule, and then I get it to people?
Yeah, that's probably the way to do it. And then person per second. No.
Let's see, converts a second to person, and that converts.
Yeah, that's probably the way to, because we want to end up with time. So somehow I was getting rid of time when I shouldn't have. What I should have done is come up with a strategy first before I just went right to the calculation. I didn't follow my own rules. But you guys know what I did wrong, so there you go. Here, let's make sure that the key has the stuff in there. I mean, this kind of problem, this is why it's on the GMAT. I don't know what, I mean, it's silly, but business school people need to know how to do this because you have to organize your thoughts. I mean, when you write a business plan, things like that, you have to be able to calculate roughly, money you're going to make, how much time things you're going to need, so you have to be able to do these conversions. Let's see.
Around 3 million years.
Yeah, it's a long time. It exemplifies how big Avogadro's number is. There it is. So 6. So yeah, they started with the P. No.
Yes, sir.
They started with. They didn't do it in one go. So they started with 6.5 billion, which is the number. Yeah, they started with people, counting 1 molecule per second, which means 6.5 times 10 to the 9 molecules per second, and then they figured out, well, if you're counting this many molecules, that's how many seconds it's going to take, and then they converted the seconds to years. So 3 million years.
I try to do it in one go because that's how my brain thinks. So start with Avogadro's
Yeah.
divided by the people. With the people, you need one person can count 1 molecule per second.
Cool.
So then, because that's underneath that,
Yep.
This is in the numerator, divided by 60, and then just converting to years.
And it works, yeah. Cool. Excellent.
Is that right?
I think so. I think so.
Can I take a picture of that? Is that?
Yeah, I mean, it's accessible
So-
on D2L, but you can
Oh,
take a
then I'll
picture.
get it.
You can take a picture, it's fine.
It's okay. I'll just look at it. If it's in there. Find it.
Yeah, it's in the test prep section of the main content area.
Alright, so, on the quiz, there was one that had the conversion factor from, what was it, iron sulfate, or iron nitrate?
Oh, okay. Hold on a second. Here, you come over here. Here. You have a pen? Just go sit over in that little corral area.
Yep.
Thank you. Take it easy. Okay. Just so over where the computers are, the one that's on, just sit in that area. Yep.
So for some reason my brain stopped working when it got to that question.
Okay.
I just didn't know how to do,
Which one?
how many moles of nitrate?
Nitrate. Okay.
Yeah.
So, again, if you ever see a problem where you're given something of a sample, like this is iron nitrate, but we want not iron nitrate, we want something different. just
Yeah.
nitrate.
Mhm.
That in your head, you should be going, I need to do a mole to mole conversion. So you have to get this number to moles somehow first. And once you have this in moles, we're going to set up a molar ratio. So let's just do it on the board.
Thank you.
Oh, yeah, no problem. So 2.36, sorry, 23.6 kilograms. So first convert to grams because you can't do you can't convert to moles in kilograms, it has to be in grams.
Okay.
So 1 kilogram is 10 to the 3. Now if I have grams of iron nitrate, I can convert this to moles using a molar mass. So we use the periodic table and, figure out a molar mass of 55.847 of iron. And there's 3 nitrogens. So plus, in parentheses, 3 times 14.0067. And then there's 9 oxygens, 3 times 3. So 9 times 60, let's do 15.9994. So the molar mass, 241. 0.86 grams per mole. So this will give us moles of iron nitrate.
Okay.
Now, the next step is the key step. So I'm going to write, this is moles of iron nitrate. But I don't want moles of iron nitrate. So I'm going to use a molar ratio where the moles of iron nitrate in the denominator cancel out with the moles of iron nitrate that I have right now. And what am I looking for? Well, what I'm more interested in is just nitrate. Nitrate ions. So how do we get this? Well, this comes from the formula.
Okay.
I look at, if I have one formula unit, one of these things, how many nitrates are in there?
We got one. Oh, in that? 3.
3 of them, yeah. So 3 in here. So you're going to get 3 nitrates for every one of these units, these formulas.
Oh.
That's the key step. Now we've converted to the new substance, nitrate only. And now I can do what I want with it. So how many moles? That's it. That's all I do. I stop there. But you could get grams, you could get actual numbers. So
Damn
using
it.
Avogadro's number. But yeah, that's the key part, the molar ratio.
For some reason, I thought I had to change it to molecules, to atoms, and then.
So unless they're specifically asking for a final answer, how many atoms or how many actual ions,
Mhm.
that's the only time you need Avogadro's number.
Okay, yeah, because everything. I feel like I was good with all this up to right here.
I mean, we'll do partial credit.
Oh, I didn't even write the answer. I completely gave up. I
Okay.
kept on going in a circle,
Yeah, no, I get it. Yeah, that's okay.
and
Better on the quiz than on the exam.
yeah,
So
that's crazy. Dang it, it's that simple. Dang, yeah, because I was thinking this, because I knew it was 3 nitrate, and I was thinking I had to get 3, but I had to put it in atoms for some reason. Because there was 3 atoms in that,
okay.
yeah.
I mean,
now
you
see
can
it.
also do it for atoms. You know, the question could have been, how many moles of oxygen atoms are there? And then you would have, instead of calculating nitrate, you would put oxygen up here, and you would have said, oh, there's 9 oxygens in this formula. So 9 to 1. Or if it was iron atoms, you would look at this and you'd say, oh, for every one of these, there's 1 iron atom. So it's a 1-to-1 ratio in the bottom. So you can pick out any piece of it
Dang.
to find it's okay to find what you want.
Dang.
So we're gonna in intro chem you probably learned stoichiometry too, where you do whole equations, reactants and products.
Yeah.
It's the same idea. We're not gonna do that until a little later, but
I gotta review all that. I haven't taken intro chem in a year or 2.
that's okay. I mean, you're getting it now, hopefully.
Yeah. Awesome. Well, thank you so much.
All right.
He forgot his.
Oh,
I need it.
there's another one in there too.
Oh.
Yeah. Thank you then.
Yeah, of course. Take care, guys.
Take it easy.